Hey there. Today I want to try something a little new on this channel. I'm going to start making little sets of videos that build up to more complex ideas by the end of the series of the videos. I'm doing this for a couple of reasons. One, I think it's a lot more digestible to go through problems like one step at a time, and also to just present my ideas more clearly and coherently in shorter, more digestible chunks. So for this set, I'll call it bouncing particles and ideal gases. We're going to try to build up to this idea that the pressure of a gas is related to its root mean square speed, which I've indicated in this box up there. That's where we're trying to head. We're trying to relate a macroscopic property of a gas, like the pressure, with its root mean square speed, which is a microscopic property of the gas. And so for the first step in this process, this will be the first video, I want to imagine a single particle in a box, like here on the left. And I've written down a couple of rules for this situation. So first, the particle's collisions with the walls are elastic. That means that energy is conserved with every collision. The particle itself is of negligible size. The only interactions that the particle has with the walls are its short-range, instantaneous collisions. Now, if a couple of these ideas that I said sound like the assumptions that you make whenever you discuss an ideal gas, they should, because those are some of the ideas that we're working with right now. So for this first task, we're going to try to average the force from the ball's collisions on one of the walls over the time between collisions. And so what does this mean, right? So if I were to draw a graph of the absolute value of the force on either of the walls over time, we would get a graph that looks something like this. And each of these spikes for the force on the wall indicates basically when the ball comes in and hits it, right? So if I would look at the right wall here, I have my ball coming in and slamming into the right wall. And so the wall is going to push the ball to the left until the ball bounces back with the same speed that it came in. Why does the ball exit with the same speed that it came in? Well, that has to do with elastic collisions. In order for energy to be conserved, if the wall is not moving, then the ball must have the exact same speed after the collision as it had before. That maintains the same amount of energy over the course of the collision, right? But you can see that these are spikes, and in fact, we're not exactly sure what the shape of the spike is over the course of these collisions, but it doesn't really matter, because one of the assumptions that we made is that these walls only involve short-range, instantaneous collisions, right? So in fact, these little changes of time over the course of a single collision is actually very, very, very tiny. So these little spikes here would look a lot closer to actual lines. Now, the goal of the problem, right, is we have all of these spikes here. We want to smooth this out, basically, and just get like a nice straight line, so that we were imagining that we were just distributing these forces over time and just averaging it out, right? And so there's a couple of ways that we can think about doing this. Since this is a repetitive process, right, the ball just comes back and forth to the same wall over nice, neat time periods, we can tackle this problem in a couple of ways. I'm going to go ahead and define kind of, I guess, like the region of my loop. So let's call this point here A, and let's call this point here B. And I'll go ahead and draw a little picture so that we have an exact idea of what A and B represent. Let's say that, let's go ahead and use the right wall again as an example. So here's our box. And here's point A. This is going to be at the start of one of the collisions, and our ball or particle comes in with speed vx. So this is A. And then B, of course, is the exact same event at some later time. So some time goes by. And then we basically get the exact same picture at B. All that's happened between A and B is the ball has gone through, hit this wall, bounced back, hit this left wall here, bounced back, and then returns back to B. So we might have a couple of ideas on how to tackle this problem of averaging these forces out now that we've established what A and B look like. And one idea that you might have would be calculus related. And we know that if we have some function, in this case f wall, if we wanted to average f wall out, and I'll notate that with this bar symbol above it, we could go ahead and take the integral of our function from B to A, let me write that there we go. Integrate our function with respect to time, and then divide by our change in time, right? And that's one very complicated way of looking at this. But I think a much easier, much simpler way to look at this is to recognize that this guy here, this guy is just our change in momentum from B to A. And so we could also write this as the change in momentum from B to A over the change in time from B to A, right? So if you think of either of these methods in tackling the problem, those are both equally valid and great ways to think about it. So let's go ahead and compute the change in momentum from B to A, which really involves only a single collision, right? The ball comes in, collides with the wall, and then after that, the wall has no interaction with the ball for the rest of the time. So we need to find that change in momentum. And so as we can see from the picture over here again, that let's go ahead and note that our change in momentum, we can write this as P final minus P initial. Oh, and let's go ahead and indicate that this is for the ball first. And so our final momentum for the ball would be negative mvx. Negative because the ball is moving to the left, and we would subtract a positive mvx because the ball is moving to the right initially. And so we would get a negative 2 mvx for our change of momentum of the ball. Now remember by Newton's third law that the change in momentum of the ball equals the negative change in momentum of the wall, right? Every action force has an equal and opposite reaction force. And so, and so the change in momentum of the wall would be a positive 2 mvx. All right, very good. We just solved for one of the components in this equation, right? This change in momentum of the wall is delta P from B to A. Okay, for our change in time, I'm going to be very explicit, and in fact, I'm going to draw another picture here. So now our goal is to find delta t from B to A. And so in this picture, right? I'm going to draw the situation right after this ball has collided with the wall, so it's going to be moving to the left. And I just want to be very careful in how I'm going to define my coordinates. So let's go ahead and draw an axis through here. Let's go ahead and call this position here, I'll do this in like blue. This guy here is going to be x equals 0, and this guy here is going to be x equals L. And so we're going to find the change in time for this first part as the ball moves from the right wall to the left wall. So, and I'm going to call that delta t1, how about? So in order to do this, Vx is going to the left, so we have a negative Vx equals, and we know that this is equal to our change in time, which is x final minus x initial over some change in time. So that would be 0 minus L over delta t1, I said I was going to call it. And so we get that delta t1 equals negative L over negative Vx, or just L over Vx. So there's the first change in time. And then for our second situation, right, is just going to be the ball returning back to the wall again. And so all that would be is just our signs basically switched, and we would get a positive Vx equals L over delta t2, I'll call that. And so I get that delta t2 equals L over Vx. So for our total change in time for the ball to return back to the wall and collide with it again, we get that delta t BA equals delta t1 plus delta t2, which equals 2L over Vx. You could easily come up with this conclusion without being as explicit and careful about signs as I was here. But I think thinking in this way and segmenting it is useful for a future video, actually. So that's why I'm tackling it like that, very explicitly. But now we have both of our components, and so we just have to plug them in to this guy right here. And so we get that this term here equals 2mvx over, what did we get before? 2L over Vx. Our 2's cancel out, and we get that this term equals mvx squared over L. So for the right wall, this term happened to be positive. For the left wall, the time averaged force would be in the negative direction. However, at the end of the day, for pressure and whatnot, we really only care about the absolute values of things. That's why I was talking about the absolute values of our forces. Now, I just want to be super clear about one other key assumption that we made, which was that the particle itself was of negligible size. This is a pretty important assumption because basically if our particle wasn't of negligible size, that would change the length that the particle would travel. So what do I mean by that? Let's say that the particle actually took up space, and so this is what it looked like at its endpoints during the collisions. Then you can see here that if this is the center of the particle, then the actual distance that the particle is traveling between these two parts of the wall is just slightly less, right? So I just wanted to draw that picture very explicitly, but you can also see that if the size of the particle did matter, this could be something that we could account for by just basically subtracting out a term based on the particle size. So, with all of those details very clear, the next video is just going to be a little step up in difficulty, And instead of talking about one particle, I'm going to be talking about two particles. Thanks for watching.